36,000 tons of steel, 343 meters from valley floor to pylon tip, 2.5 kilometers across. This is how a road floats above a river. The Tarn Valley in southern France cuts deep into a limestone plateau. For decades, drivers heading south crawled through the town of Millau below, snarled in summer traffic. The solution chosen in the late 1990s was extraordinary. Not a tunnel, not a detour, but a bridge that would skim above the entire valley. Design work began in 1987. By 2001, after years of studies and competitions, the first convoys arrived. A concession contract handed the project to Eiffage. No public money. The company would build and operate it for 75 years. On October 10, 2001, surveyors set their first stakes on the plateau. The valley they were measuring would soon hold the tallest bridge ever built. The first task was the foundations. 7 piers would carry the deck across the valley, each anchored deep into the bedrock. Crews opened wide pits along a precise line drawn between the two plateaus. Excavators stripped topsoil, then bit into the harder limestone below. Sheet piles braced the pit walls. Survey teams checked elevation against the design model dozens of times a day. A single misalignment now would ripple through every pier above. Concrete pump trucks moved into place along access tracks cut into the slope. The valley floor, once pasture grazed by sheep, became a corridor of yellow machinery and dust. Eiffage planned this phase tightly. The total construction window was 38 months, and every week of delay shortened the operating concession on the other end. By early 2002, the pits were ready to receive the reinforced steel cages that would lock the piers to the ground. Inside each pit, ironworkers tied together massive cages of reinforced steel. The bars rose in dense vertical bundles, bound by horizontal rings every few centimeters. From above, the cages looked like rough cylinders waiting to be filled. Crews then erected timber and steel formwork around them. Concrete arrived in continuous pours to avoid cold joints between layers. The piers were not solid blocks. Their cross-section was hollow, walls only 60 centimeters thick, designed to flex under thermal loads and wind. Engineers had calculated that a solid pier of this height would crack under its own movement. The hollow box shape distributed stress and saved enormous weight. Above the foundation, each pier began to climb. A self-climbing formwork rig sat on top of every pier, lifting itself by 4 meters whenever a section had cured. The structures were still short, barely above ground level, but the geometry was already locked. By mid-2002, the 7 piers stood as clearly defined verticals along the valley floor. Each one was hollow concrete, gray and clean, rising on a precise schedule. The self-climbing formwork repeated its cycle. Pour, cure, jack upward, pour again. 3 days per 4-meter lift, sometimes faster. The pier shafts tapered slightly as they rose, narrower at the top than at the base. This was structural, not cosmetic. The taper reduced wind load and put the bridge's weight where it was easier to carry. At ground level, the bases were 6 meters thick on each side. Workers moved between piers along temporary access roads. Tower cranes followed each pier upward on their own climbing schedule. From the plateau edge, the project began to look less like a construction site and more like the skeleton of a future structure. The tallest piers were still a long way from finished height. Through 2003, the piers climbed past 100 meters, then past 150. The 2 tallest, anchoring the central spans, were headed for 245 meters above the valley floor. At those heights, weather became an operational concern. Wind speeds at the top of the formwork could exceed 60 kilometers per hour while the ground stayed calm. Work stopped above certain thresholds. The self-climbing rigs continued their slow vertical march, each one a small factory perched at the leading edge of its pier. Concrete was pumped through pipes running the full height of the structure. Verticality was checked constantly with GPS sensors and laser systems. A deviation of more than a few centimeters at the top would compound into a serious problem once the deck was placed. The piers were not yet topped out, but they had already become the dominant feature of the landscape. By early 2004, the piers had reached their final heights. 6 smaller ones flanked the 7, ranging from 77 to 140 meters. At the top of each pier, A temporary launching pylon was bolted in place, a slender steel mast that would support the deck during the next phase. On both plateaus, far from the valley itself, deck assembly yards came alive. Steel deck segments arrived from factories at Lauterburg and Foss-Surmer, traveling by road on